Can you all hear me? Okay, everything good? Volume? Okay. Yeah, I'm Dominic Perini. I'm a technical lead and scalability architect for a company called Erlang Solutions. It's a company that focuses its effort particularly on the Erlang language. How many of you have heard of the Erlang language before? Can you please raise your hand? Okay, not that many, but yeah, it's a functional language. It has some interesting features, and I would argue that some of the most interesting feature is the VM. It is a VM that works very well with scalability, and I will try to explain why. But in this talk, I'm not going to focus particularly on Erlang or elixir. This is a high-level talk that goes into how to build systems that scale. Right. So a little bit about me. My experience comes from Sony PlayStation. I led the backend development team for a game called Little Big Planet. It's one of the major franchises of Sony. At the time I left, it had 16 million users registered, 12 million user-generated content, and on behalf of Erlang Solution, I led a blockchain research and development team for a global credit card payment provider. We reached 4,000 transactions per second to support more than 15,000 worldwide connected financial institutions. And our effort led to some patents being registered. And I also led an organization which I founded that is focused on natural language processing research and development. And I cooperated in a consortium in partnership with the Metropolitan Police of London and the Police of Madrid in order to aid the police investigation. So analyzing police statements, witness reports, find element of corroboration or contradiction at the semantic level. And I'm currently working on a novel approach for highly customizable smart contracts. Okay, before we get into the talk, I'd like to introduce a few persona that you might have to deal with in your quest for scalability. The visionary, decision maker, arguably controversial, and opinionated employees, typically inexperienced developers that think they know more than they actually know, biased ops engineers that think they want to stay on the safe side, not use any particular ideas because that might lead to extra work. And yeah, in this respect, real metrics, measurements, benchmarks are far more useful than getting influenced by some of these guys. And another message is there's no magic. Nothing happens by magic. There's no replica happening remotely by magic. There's always a networking layer involved. So the goal is to seek performance, but avoid giving up reliability. So, and we know that nothing is 100% reliable, but we can aim for approximation of 100% reliability. When it comes to horizontal scalability on top of the vertical scalability that we probably all know about, is purchasing more powerful hardware and scale vertically. The horizontal scalability involves multiple physical machines, virtual machines, containers, and the connectivity among those. So there might be a local connectivity, there might be a TCP and RDMA, remote direct memory access. And typically now the language shifts from data center rack, physical machine, into cloud computing that has the notion of region, the notion of availability zone, physical machines and virtual machine and containers stay pretty much the same. So an availability zone is an area, a confined zone in which there's intention to confine failures. And obviously, there might be connectivity issues kicking in, and also aside from the individual machine or instances failure. So even the on-premises or in both, also the cloud data centers can suffer a split plane. So in these circumstances, we lose connectivity among clusters. And same goes for zones or racks that lose direct connectivity. So there could be a fallback connectivity that can be explored that uses the broader internet when direct connectivity is lost. So two data centers might not have the direct high-speed connectivity, but we have a route that goes over the internet. Alternatively, we can have a dedicated fallback connectivity. And this is a valid strategy to regain control on resources that are under attack. So suppose you are under pressure because there's a denial of service attack going on, and some attacker managed to get hold of some of your resources. With a fallback connectivity, you have another way to regain control of those resources. When it comes to data distribution strategies, this is again in order to get better scalability. We seek scalability by tuning consistency and availability. And we use some strategies such as sharding that introduce better horizontal performance so that there is no congestion going on excessively on single instances. So, but the load is spread out, is sharded out. And there's replicas which can also introduce extra performance because suppose there are consumers that consume data in read mode from the replicas, they can do it from several replicas in parallel. And also replicas allow you to recover from failure. So typically this setup goes on to either master-slave mirroring or a consistent hashing distribution. And here I would like to ask another question. Who has seen this before? Please raise your hand. This ring. One person. Wow. All right. So this is also known as the dynamo ring. It's a way to segment your data. Typically, this is segmenting an ID of the data, and so all of these segments get distributed over some instances on some nodes. So here the color indicates, for example, the green indicates that everything goes on node 0. The orange indicates that it goes on node 1, etc. And obviously this is the primary location of this data, but there could be a replica on another node. And when we have a distribution model following the consistent hashing, we can use a variety of strategies for writing, reading, and mitigating errors. So typically, the approach for write and read follows the quorum approach. That means that if you have replicas in the region of 3, you are safe to write to 2 and read from 2, and you are always guaranteed to have the latest data. And also, in the event of a split brain, it means that only the segment that reaches the quorum progresses. The segment that is in minority stops because it cannot reach the quorum, therefore it cannot perform a write or read. There's a distinction between write and read because write, regardless of what strategy you use, will write to every replica. But the read only stops when it reaches the quorum, for instance. And interesting is a handoff migration strategy that can be introduced on top of this. Suppose one of the node fails, and we create a new instance for that node. and we start migrating some of these segments from the healthy nodes into the new node that we spawn, because we know that the other node is gone. And this can mitigate and help repairing failures situation and mitigating the split brain. Typical mistakes into this strategy is putting replicas everywhere. So, as I stated before, there's no magic, so replicas are using network in order to allow this replication. So imagine that there's a cluster that is already close to peak, and has got n instances, and you say, okay, I want to add another instance to improve the situation. But actually, if you go replicas everywhere, the situation gets worse because of the extra traffic that this generates. Another mistake is repairs targeting a single node. So if a node disappears and the recovery implies that there's a handoff coming from a single node, that healthy node might be affected by this extra request. So it's a good strategy to spread around this request for repair. In terms of auto-scaling and triggering immediate handoffs, this is also a mistake. So typically, if you have an unstable cluster that changes its shape frequently, it's not a good idea to kick in handoff mechanism or repair mechanism right away. Because suppose that a machine gets added and yet another machine gets added, so there might be a migration of some of these segments going to a machine, but actually the final location is somewhere else. So there's a cascade migration kicking in, which is unhealthy and can lead to instability. In terms of network topologies, we are all familiar with the star approach. It's probably the first that was used in the industry, and then obviously there's a decentralized effort that is aiming at reducing the congestion on a single node. And there's the distributed one, which is typical of a peer-to-peer network. There's also a chord approach, which uses a finger table that keeps connection with neighboring node. So in this case, A and B are two nodes that are not directly connected. But there are a few hops that you have to go through in order to reach your destination. And then there's the full mesh, which is an interesting network for distribution. And this is the Erlang distribution, for example, uses this method. And I will explain now why it's interesting. So it follows that progression in terms of how many connectivity you have. So it's a triangular series of connectivity. As the node rise in number, you have a corresponding number of connections raising as well, which is growing much faster than the number of nodes. So the good characteristic is that every pair of nodes has a direct route and a number of indirect routes, and is suitable for running gossip protocols on top of it. These gossip protocols allow you to detect quickly a failure and apply countermeasures, some repair mechanism, or, as I stated before, a handoff. There's fewer hops because every node can talk directly to another node. But generally, this implies that there is more traffic. So I mentioned a gossip protocol before. A very basic elementary gossip protocol might be a protocol that says I'm alive, and one of these nodes can communicate broadcast to every other node in the network that he's alive. So in the case of 12 nodes, you have 66 connections. So you got suppose you have one gossip that goes 1 message a second. So there's 12 by 66 a second messages being sent around. And we understand as this network grows, there's a lot of messages going around related to gossip. So it's not desirable to have very large, fully meshed network. When it comes to consistency, we are all familiar with strong consistency. This is typical of relational databases, SQL databases. There are other databases that use that model of distribution related to consistent hash. So these other databases expose an eventual consistency, which is the lower level of consistency. So we have traded in some consistency in order to get better availability and scalability. So I can name Dynamo. This is probably the one that introduced this concept. DynamoDB from Amazon, but there's also Cassandra. There's a variety of this database. In the Erlang space, there's Riak. Yet, for example, Riak is interesting because it's got an additional level of consistency on top of the eventual consistency. So strong eventual consistency is slightly higher than eventual consistency, but is not at the level of strong consistency. This typically uses conflict-free replicated data types. We got two flavors typically of replicated data types. In some circumstances, we can apply to commutative non-idempotent changes a distribution of the function of the operation that gets applied to the data. We just have to ensure that there's no duplication. For example, this might involve charging a bank account of €10, and we have to ensure that this doesn't happen twice. But again, the order in which it happens, if you have two charges, one is €10, the other one is €20, it doesn't matter in which order they happen, as long as eventually they happen and there's no duplication. It doesn't guarantee that your bank account doesn't go in negative territory. So if you're happy with that, it's a good extra degree of consistency that can be applied. And relatively inexpensive. And another one is the one that involves a state distribution, which is applicable to data that can have operations that are commutative, associative, and idempotent. So, for example, if you add an attribute to a type of data, it doesn't matter in which order it happens, or if it happened twice. Eventually, this state can be merged. And yeah, the example about bank account, I already made it. So let's move on. When it comes to concurrency, we have Erlang uses an actor model, which is an interesting model that goes hand in hand with functional programming. Functional programming has typically a message passing sort of approach and state isolation. Erlang certainly has. So, it's a system, it's an approach very suitable for distribution. But it's not the only one. And in terms of concurrency, we might be interested in having more close to the bare metal sort of concurrency in some circumstances. So we have a shared state. We can reach higher performance because we access the same memory. In some circumstances, it might be difficult because when you write, you start talking about locks, you start talking about operations being blocked by others. But when you read, is particularly good. For instance, if you have an algorithm that harvests on top of a segment of memory, this is good because you can allocate the memory once, you have a lower memory footprint, you have high performance, and in fact, this is the model that is used for GPU computation typically. So when it comes to handling of failures, yeah, typically the exercise involves identifying and avoiding single point of failures, so ensuring a sufficient number of replicas in place, and putting in place a retry mechanism. So if a request has failed, you can try a second time. So there's a synchronous and asynchronous way of handling this. So the synchronous is timeout based, and your requesting process sits there and waits until it receives a response and then times out. Or the synchronous approach is you fire a message, then you start doing other things, and then you wait for the acknowledgement coming back. If this acknowledgement doesn't come back, then you are in a position to exercise a retry. There's a note here that for failures that are caused by high throughput, so excessive pressure going into the system, retry is making the situation worse. So you should have a decaying frequency sort of retry so that the system cools down and starts operating. Otherwise, if you have a too frequent retry, then you might get the situation even worse. Another note, this is typical of developers that like to pass the buck and say, okay, if my system doesn't perform as we agreed, try again, but it's your responsibility to try again. I rather have systems that guarantee that they can recover by themselves. So, moving to the next slide, on a robust system, we have an ingestion that should happen very fast, and the data ingestion should be tracked and replicated. And tracked with an ID, so that we give this ID to a customer, and our customer can come to us and say, what happened with that data that I sent you? Here's the ID that you gave me. Can you check what happened? And you can say, okay, it got stuck because I had a failure, but now it's recovering. Expect it in the next half an hour or something. Yeah, recovery strategy should be in place, and adaptation. We have heard of auto-scaling, and this can be driven by metrics. Typically, cloud providers use the metric of the CPU. So when there's an excess of CPU usage, they trigger an auto-scale. There might be more clever metrics and more clever approaches to auto-scale. And we have to ensure that provisioning external resources is fast enough. So otherwise, if there is a cache warming involved that is taking too long, if there's a ramp up of connectivity taking too long and too many processes having to be spawned, these new resources might not come up in time in order to handle the excess of load. So another strategy could involve a reduced level of service. So at the optimal performance, the system can deliver a certain number of services. When it has an excessive number of requests, it can stop serving some of the extra features, but still it serves some of the features. It's better than nothing. And back pressure control is another mechanism that can be applied to metrics. So this comes from load testing. So once you load test your system, you understand that it goes up to a certain level of throughput. You set a threshold there, and when you are close to that threshold, you stop getting extra traffic, because you know that if you go over the threshold, your system starts degrading, and you have less service. In this case, you can have your system working at its optimal performance for a prolonged time with this back pressure control. An example, this is an example of blockchain, peer-to-peer network, trustless, permissionless. This is used, as many of you, guess, know, to trade fungible and non-fungible tokens and exercise smart contract automation. And it's a system that is very challenging from the scalability perspective, and also is particularly exposed to malicious actors because it's spread over a large network. When it comes to consensus approaches, I had experience working with Paxos. Paxos comes in two flavors. One is leader and one is leaderless. It's interesting because if you have a distributed network following that full mesh distribution pattern, you can avoid using gossip. So in fact, the leaderless approach doesn't need gossip to run. This is somehow attractive because when we have a leader, yes, a leader election involves fewer messages going around in the network because there's only the leader generating these messages. However, there's an inherent single point of failure there, because if the leader has started informing the rest of the network that something is happening and the leader falls down at that time, you need to have your countermeasure to recover from that situation. Raft is a simplified version that always involves a leader, and proof of work, we know it. It's an interesting mechanism to provide a consensus that is decentralized, but we know it uses a lot of energy and does not scale. It's Bitcoin and Ethereum are still in the range of 5 to 15 transactions per second. And I conclude with some recommendations. So the good idea is to know your use case very well and know your tools. You should be able to question yourself, would you be able to reinvent this tool? Do you have a sufficient understanding of the infrastructure that you're running your tools on? Do you have a sufficient evidence that the tools that you have chosen meet the demand? And always have a plan B. So an API to swap out a component in favor of another one, and that fallback connectivity that I mentioned before. Now, if we have questions, I'm more than happy to try to answer. Thanks. No question.